welcome everybody. So today I'm going to talk to you about PES, which is also known as Photoelectron Spectroscopy. And so the purpose of this technique is to determine the ionization energy of all of the electrons in a given atom. And so what happens is basically we're using a photon of energy, and we're going to use high energy photons. We are going to bombard an atom or a series of atoms with these photoelectrons, and we are going to remove basically all of their electrons. The idea is that we're going to use these high energy photons. We're talking about X-rays, we're talking about ultraviolet light, and we're going to have the atoms in a gas phase. We're going to irradiate them with the photons, and all those photons are going to have the same exact energy. As long as the energy of the photon is greater than the energy of the electron, which it should be, then it can remove that electron from the atom. Now, when I do the math for this, the energy of the photon, it is equal to that ionization energy, the energy required to remove the electron, plus the kinetic energy of the electron that can be detected by a detector. And so, if I rearrange this equation, I can determine the ionization energy. It's equal to the energy of the photon minus the energy that the electron has once it's ejected. Now, you don't have to know this math, really. We're going to stick to the concept, the idea of, looking, well, what's the usefulness of this technique? Something that's important is that, the photons, they have a sufficient amount of energy that's being used. If they don't have sufficient energy, then the electron will not be ejected. As long as the photon has sufficient energy, it will eject an electron. It's akin to the photoelectric effect. So we're going to have a large group of atoms. All of the electrons that are ejected from a particular energy level are going to have the same amount of kinetic energy coming off. But what we're going to see is that this will hold true for sublevels as well, and we can actually determine the number of electrons in each sublevel. So we can do it based on energy level, but then we can even subdivide it and do it based on sublevel as well. So what we're going to get is we're going to get this Photoelectron Spectrum, and we can actually plot the number of electrons versus what their energy is, their ionization energy is. And we can determine how many electrons there are in an atom. We could determine the ionization energies for those electrons. It's really kind of neat. So what is this going to look like? Well, let me show you. Here shows you a photoelectron spectrum for a particular element. And so what I see here is that this is the relative number of electrons right here. And then this is their ionization energy. And notice the units, it's megajoules per mole, not kilojoules, it's megajoules per mole. So the values are smaller. Now, the scale for the x-axis is actually backwards, it's high to low. So you could think of this part right here as being where the nucleus is, and this almost as distance. So these electrons right here, these are closest to the nucleus. So these would be, for example, like my 1s electrons. They're the closest electrons that there are. The next electrons, notice they have a big break here because there's a huge difference in energy between the two levels, would be 2s electrons. And then the next set of electrons would be 2p. Now, what element would this be? Well, 1s and 2s, they have the same relative intensity. But then 2p here, it looks as though it's 3 times the intensity. It looks like it's 3x in terms of relative number of electrons. So it looks as though there would be 6 electrons for 2p, 2 electrons for 2s, 2 electrons for 1s. And so our electron configuration would be 1s2, 2s2, 2p6, and this would be neon. So this allows us to see all of the electrons that are being removed from an atom. If you go and you research neon's first ionization energy, it's around 2000, and we see that these 6 electrons here, they are all being removed with around 2,000. Now notice that they have the same ionization energy. And that's because all of the electrons in the same sublevel have the same probability of being removed at any one time. This is a conglomerate graph that's been made over the course of doing this experiment thousands of times with so many atoms. So here's another type of question that they could ask you. So here they say the photon spectra above show the energy required to remove a 1s electron from nitrogen and a 1s electron from oxygen. So we're not talking about the valence electrons here, we're talking about the core electrons. Which of the following statements best accounts for the peak in the upper spectrum being to the right and the peak of the lower spectrum? So when we look at this, we look at the ionization energy of oxygen as being greater. So oxygen, to remove that 1s, has a higher ionization energy, and nitrogen, for its 1s, has a lower ionization energy. So why does it take more energy to remove oxygen's electron? Nitrogen has half-filled p shells. People love to pick this answer because they look at it and they're like, oh yeah, nitrogen does have half-filled p orbitals. But it turns out, okay, they're not talking about the p orbitals here. They're talking about the 1s, the core electrons. There's more electron repulsions in oxygen atoms than in nitrogen atoms. Again, this is true, but they both have the same number of 1s electrons, so it's not true for this answer. Electrons in the p sublevel of oxygen provide more shielding. Well, that is also kind of true, I guess, because there's that extra electron. Maybe if we're using Slater's equation, we would see that. But really, the nitrogen has a smaller nuclear charge. We're talking about the 1s electrons, the electrons closest to the nucleus. It has to do solely with nuclear charge. So D is our answer. All right, here's another one. Let's see if we could figure out what element this is. They tell us that it's potassium. Let's see if they're right. So again, this is closest to the nucleus here. Notice it's the highest ionization energy. 1s, 2, 2s, 2. Does this peak right here look about 3 times? I would say yes. So I would say this is 2p6. Then over here we have again something that's pretty much equal to this, 3s2, and then again 3p6 because it's about equal to the 2p6, and then this one here 4s, but now it's about half the size of the other s, so it's about 1. And there we have it. That's potassium's photoelectron spectrum. All right, so here's a question for you to think about. Let's see if you could try this on your own. A certain element being studied by an X-ray PES displays an emission with 5 distinct kinetic energies. What are the possible elements that could produce this spectrum? Determine the orbitals that the spectral lines are originating from, and determine the elements that have electrons in only these orbitals. So give this a try. We have 5 distinct kinetic energies. So see which element you think that might be, and we'll talk about it tomorrow. All right, have a great day. Thanks for watching.